Hello and welcome to this ALINT-PRO tutorial. My name is Brandon, and today I'll be showing you how to add block level constraints to your design which help improve your overall linting results in places where HDL is unavailable or non-synthesizable. These constraints will explicitly tell ALINT-PRO how certain components are to operate, and are particularly useful for designs involving encrypted IP, missing libraries, yet to be implemented blocks, or even behavioral non-synthesizable components. In fact, block level constraints can even facilitate analysis of largely hierarchical designs, as once individual blocks are verified separately, those top level blocks can be abstracted via constraints, which allows the tool to only focus on those potential input-output issues between the top layer and other components of the same design. However, you wouldn't have to worry about constraints for FPGA vendor primitives, for example, as we provide those predefined and with precompiled constraints already. So with that introduction to the topic out of the way, let's go ahead and get started. We'll first begin in this very simple design composed of a single D flip-flop. As you can see, only the interface is defined, as I've yet to implement the actual logic. In fact, we can see from the schematic that ALINT-PRO will just consider this instance by itself a black box, meaning the tool can see the I/O pins, but the logic within is unknown. Obviously, this makes analysis difficult. As is, this component wouldn't provide proper linting results within a design, and we therefore need to tell the tool what this component is. We'll do this by creating a constraints file, which can be created and added to your project like any other file. And within this file, we will write commands to specify our constraints. The ALDEC design constraints themselves are actually ALDEC's extension to Synopsys design constraints, and therefore share similar syntax and command names. Meaning if you know SDC, it should be pretty easy to get started with ALDEC constraints. So applying that to our design, this module is supposed to act as a flip-flop. So we'll therefore use the setCell command with the kind argument specifying flip-flop. And to specify the exact cell for this constraint, we'll use the getlibcells command, which returns all cells matching this name within this library. So now the tool expects a module with flip-flop behavior, but it does not necessarily know what ports correspond to those of that type of logic. This is where the createCellClock and setPin arguments come into play. The first command here is simply creates the clock for the cell, and we can specify whether it is falling or rising edge. Additionally, we can see the getlibpins command here is used to specify the exact pin we're referring to. The hierarchy here goes library, module, pin. Next, using these setPin commands, we can pass the behavior for each pin via the kind argument. As you can see, our input data pin is set to input, our enable pin is set to enable, and so on. And finally, in these last two lines, we can see a conditional statement. Depending on the cell's generic, we are either going to have a synchronous or asynchronous reset on our flip-flop. We can see here that the $ symbol is used to access those generics. So now that our constraints are written, we can go ahead and rerun our flow here. This time, ALINT-PRO knows to treat this stub as a flip-flop due to the constraints that we just wrote. So once finished, we can go ahead and look at the schematic once again. This time, the cell is displayed as a conventional flip-flop and no longer a black box. And all that was needed were those setCell and setPin commands. Let's now move on to another example which utilizes a black box within a design. The project I have open here consists of an asynchronous FIFO that's acting as the synchronizing mechanism between two different clock domains. Despite this, we can see via our violations that no synchronization is being done, among other issues related to connecting signals to black boxes. And this is because the FIFO that I'm using is a generated IP, and the body is encrypted so we can't access the HDL to perform proper linting. Instead, we have access to a stub file, which results in this black box within our schematic again. In fact, looking at our synthesis report, we can see a number of black box connections for both inputs and outputs. And at the bottom, we can see a list of our black boxes. With all of this information connecting to our as of yet unknown module according to the tool, we will not be able to properly lint this design, and we therefore need to add constraints to this module. One way to add these constraints is how we did before, using the setCell and setPin commands. However, due to the multiple clocks, additional commands will also be needed to constrain the different inputs and outputs to their respective clocks, via the setInputCellDelay and setOutputCellDelay commands. So there we can see data in gets sampled by our writing clock, while data out is sampled by our reading clock. While this method of constraints will do the job for pretty much any black box, we can actually minimize our commands for more common logic types, which this FIFO does fall under. So I'll go ahead and quickly add the proper constraints, and we can see that this time we only have to input a single command. There's only a set cell command, no set pin commands. And this is because we're passing a function, the library async FIFO function. There are functions for many common components, and they each have their own set of arguments relating to their pins. Using the arguments, all we have to do is pass the module's pins, using the getlib pins command again, to the relevant argument. So here we can see all of the pin types associated with this type of module, and all of our actual module's pins. Of course, to see what functions like this are available and what their arguments are, we can always refer to the command reference guide. And under library functions, we will find more detailed information on each command. In fact, we can see a library function for a D flip-flop, meaning for a shorter constraints file, we could have used this instead of our set cell and set pin approach previously. Additionally, more information on our general constraint commands can be found here too. So now that we've specified our FIFO's functionality within the design, let's go ahead and rerun our project. This time, our constraints will be applied to our FIFO, and as a result, we should no longer get those violations about connecting signals to black boxes, or issues with data not being synchronized across clock domains. So with the process done, we can take a look at our violations and see that most of those violations have been cleared. The only one remaining is that issue with synchronization across our domains. In fact, let's figure out why we still have this violation. We can see the cause of the violation within the schematic, and from this view, we can see that our FIFO was in fact properly constrained, as it is no longer a black box. Looking at the source of our violation, we can see that it comes from our 100 MHz clock source, and the data is being written using our 75 MHz clock, which is causing the violation. Our read and write clocks are switched. So let's go ahead and fix this issue by inputting the correct clock signals to our FIFO. And once corrected, we'll go ahead and rerun the project. Because of those constraints applied to our stub file, ALINT-PRO was able to properly identify that true error within the design, as it recognized the incorrect use of our synchronizer, despite it only being a simple declaration of inputs and outputs within actual HDL. So with the error corrected, we have cleared that previous violation, as the tool now properly recognizes our constrained FIFO as the synchronizer in our design. Let's now finally go over our synthesis report again to see what's changed. Going to our inputs, we no longer have signals connected to black boxes, as our read and write enable signals have now been properly constrained. This is true for outputs as well. And finally, we no longer have any black boxes detected, and instead we just have this gray box, meaning this particular module, the FIFO, is no longer unknown to the tool. Its behavior and role are properly described via our newly added constraints. And with that, that'll actually mark the end of this introduction to block level constraints. I hope this video was informative, and of course, thanks for watching.